And we're live. Excellent. Welcome back. Today is Wednesday, the 17th. What a wonderful day it is. Finally getting some, yesterday was warmer. I was going to say finally getting some good weather, but today was cold. None of you would know that, though. All of you are still sitting in your PJs, sipping on your hot chocolate. I don't know what you're doing. But we're back. That's all that matters. If you would, ladies and gentlemen, if you would be so kind, leave me a comment in the chat for my records. That'd be fantastic. It'd be absolutely fantastic if you would. You can see the 13 people that are here. That'd be wonderful. So here is, while you're doing that, here is the outline of today. I had mentioned last week, because this is the first time I'm seeing you this week, but I had mentioned last Friday, that I was aiming towards a major. And I'm still aiming towards that major. In fact, I am going to be assigning you that major before the end of this week. Now, this major, obviously, I'm going to continue to have that kind of thing online, of course, simply because of the nature of what we're dealing with. But today, I would like to review for said major. We are wrapping up Chapter 6. Next week, we will be beginning Chapter 7. And over the course of the weekend, you will be getting done that major assessment for me. But like I said, today is for review. So, if you do not already have them out, I'm going to need those notebooks out and open. While you're getting those notebooks out and open, I am going to be posting for you in the Google Classroom stream. I am going to be posting for you a PDF of the review that I'm going to be working through today. Let me make sure that I have this thing open on my phone so that I can see the chat that you guys have. There you all are. I can see the chat directly on my phone. There you all are. It's great. It's wonderful. And I am about to post that PDF into, here we go, Chapter 6 review for today. Post. And posted. Which means that right now, you should be able to access the PDF of the review that I would like to work through today. Obviously, it's difficult to read the problems on the board, so you can follow along with what you got. And again, this is my objective for today. I would like to review. I would like to get us ready because I am going to be assigning you a major assessment before the end of this week that you will get done for me over the course of this weekend. Next week, when I see you, well, not when I see you, but next week. Actually, no, probably. I'm trying to think. Today's Wednesday. Yeah, today is Wednesday. So before the end of this week, I'm going to be assigning you that major. But then on Friday, I should be starting the new chapter. Yes. Like I said, I am going to be giving you the weekend still. That's been my objective, to get this major done. But yeah, Friday I should be starting the new chapter. Oof. And then next week, you should be back. You should be back. Who the heck knows? Unless there's another super spreader event. Teenagers. Anyway, let's see what we got here. So I'm going to flip my screen over. There we go. And like I said, in the Google Classroom stream, you should have this PDF. I know it says test form 2C and all that stuff, but that is the review that I would like to work through today. That would be phenomenal. And I have a copy of that review right here, which is great. But of course, your PDF is probably better for viewing the problems and being able to write them down. Of course, if there are any questions as we are moving along, you can throw those questions into the chat. I have that open right here. I just opened up my calculator because I wanted to use it. Let me reset that guy. There he is. He's reset. Okay. Now, I'm not going to be going over every single problem on this particular review. I'm not going to be going over every single problem, but I would like to go over the information that is necessary for getting this particular chapter done. Here we go. Now, the first few problems here are dealing with function operations. It is your job to recognize what operation they are asking you to do. For example, I want you to compare the symbols used in problem number 1 versus problem number 3. Please compare the symbols used in problem number 1 versus problem number 3. More specifically, when I say the symbols, I am pointing right here to this little dot, and I am pointing right here to this different looking dot. In number 1 is telling you to get done multiplication, just for the sake of argument. Number 1 is telling you to get done multiplication. Number 3 is asking for the composition. Those symbols are different. When you have that open circle, it is the composition function, meaning one equation being shoved inside of another equation. Whereas in number 1, it is just a single dot indicating that it is multiplication. They want you to multiply those two functions together, the x squared plus 4 and the 7 minus x. It may be helpful for a problem like number 1, and I'll kind of move this down a little bit so you can see it. It may be helpful to just multiply them together in a box, because it is a binomial times a binomial. There we go. I wanted to make sure it was visible on that screen. This is just number 1. Multiplying them together, I get a 7x squared. I get a positive 28. Ooh, negative x cubed. That's weird. And then negative 4x. Typically, the way that we write our answer, with those 4 terms, we have to combine like terms, but there are no like terms. But typically, we write it from largest exponent to smallest exponent. Let's see if I can get this on the screen here. There we go. The final multiplied answer should be negative x cubed plus 7x squared minus 4x plus 28. There were no like terms to combine there, so mer. But yeah, that was, you would have to recognize that as a multiplication function because of that dot. It's telling you to multiply f times g. And that's what we get. In terms of number 2, I'm probably going to have to, I'm going to put 2 and 3 on a separate sheet of paper simply because I want to have the room for them. But on a problem like numbers 2 and 3 are actually both asking for composition. Number 2 is asking for you to evaluate the g of x function, g at negative 2. And then the result of that g at negative 2, the result of it is going to be shoved inside of the f of x function. Now, like I said, I wanted to put this on a separate sheet of paper. So let me bring this into play. There we go. And let me write out both functions, and then we'll talk about what is necessary. This is number 2. Number 2. And ultimately, based on those 2 functions, they want you to evaluate f of g of negative 2. Move that out, move that out, move that out. There we go. So first and foremost, I'm going to work from the inside, and I'm going to evaluate g of negative 2. If I were to plug in negative 2 into that g of x function, negative 2, put parentheses around it, squared, would give you positive 4 plus 3, which is 7. Now, 7, of course, is not our answer. 7 is just what g of 2 is. Now, remember, the problem wanted you to evaluate f of g of 2. G of 2 is what should go in this blank right here. But instead of g of 2, I'm not going to plug in a g of 2. I'm just going to plug in a simple 7 because that's what g of 2 is equal to. In reality, now they just want me to evaluate f of 7, which it should be x minus 5, so it's 7 minus 5. The answer should be a 2. Composition functions need to be thought of in one of two ways. You're working from the inside out to evaluate, technically just like PEMDAS, inside out, if you're evaluating and simplifying. Or, in the case of number 3, you're going to have to put one function inside of the other. So here's number 3. With a problem like number 3, they give you a brand new f of x, and they give you a brand new g of x. They'll do that for every problem that we have here, typically. X squared minus 3. And now they want you to evaluate or simplify f of g of x. Fog. It's not the only notation they could have for composition, but that open circle implies composition. Again, this is number 3. If I'm going to put the g of x inside, if I'm going to go f of g, meaning g of x is on the inside, forcibly being shoved inside of the f of x function, the f of x function is normally a 2x plus 5. But if you notice, I left a blank there, because that blank is where the x would be. That blank is where the term would go. That blank is what number I would typically plug in, but this time around, I'm not plugging in a number. I'm plugging in an equation. I'm plugging in the g of x function, which in this case is just x squared minus 3. Simplifying is all that is needed to get this answer done. To simplify, I can distribute that 2 minus 6 plus 5, ultimately just becoming 2x squared minus 1. And move that up a tiny bit more. There we go. Excellent. Now, again, the beginning of this chapter dealt with function notation, where I asked you to add functions and subtract functions and multiply functions and divide functions. And in this case, the 5th operation, compose functions, the composition function in this case. Then we got to problems like numbers 4 and 5. Bringing this back down, zooming back in on numbers 4 and 5. Again, this PDF, if you haven't seen it already, this PDF is available in your Google Classroom stream, so you don't have to strain your eyes at the image that you see here. But numbers 4 and 5 are talking now about inverse functions. Mr. Markey, where was the connection here between all of this and square roots? Well, square roots and quadratics are inverses of each other. Let's look at number 4. They want you to find the inverse of that function. Now, if you happen to remember our notes on inverse functions, there are 3 ways to determine whether or not 2 functions are inverses of each other. And I bring that up for number 4 simply because we will actually perform one of those things. To determine whether or not 2 functions are inverses of each other, number 1, graphically, they would be reflections of one another across the diagonal y equals x. In fact, let me go to Desmos right now. Actually, you know what? No, I got my calculator here. I'll do my calculator. So basic inverse models of each other. I could do x squared and the square root of x. Now, again, unfortunately, the square root of x will only give me a half of a parabola. So I put in that negative. Here comes the graph. They're slightly different colors, of course, but that's okay. I could put in that third function, x, and it cuts it right down the diagonal. They are reflections of one another. Let me zoom in. There we go. You can see it a little bit better right there, where that diagonal does cut it straight down the middle. It's kind of nice. They can fold in on each other. Okay, sorry, I was just reading an email. Back to this. So when they say to find an inverse, I could use the graphing function, but there could be something better. Another way of determining whether or not two functions are inverses of each other, if you had both functions and you took the composition of those two functions, the result should be x if they are inverses. Well, we don't have a second function. So what's the third? Okay. If two functions are inverses of each other, then every single ordered pair x comma y would become y comma x in the inverse. Now that's what we need. If two functions are inverses of each other, then every single ordered pair y comma x is flipped around to become, or I'm sorry, x comma y is flipped around to become y comma x in the inverse. Now the way that that plays out for us here is this. We can take this original function for number 4, which I'm going to write right here. F of x equals 5x plus 10. I'll write it as y equals simply because that's a lot easier to write it as, plus those were the directions that I gave you. And if I want to find the inverse function, the first thing that I'm going to do is that inverse step where every single ordered pair x comma y becomes y comma x. Or I'm literally going to flip around the x and y positions. From here, I just got to solve for y. I'm going to subtract 10. I'm going to divide everything by 5. Now, I just kind of skipped a little bit of a step here. Technically, it should be x divided by 5, or a 1x over 5. So I made it a 1/5 x. And then 10 divided by 5 was just 2. Technically speaking, this is, I'll zoom out a little bit more. There we go. This is the proper notation for the inverse function. F of x becomes f inverse of x. Or you could call it g of x, but, you know, this is the proper notation for it. The notation that you would typically see for an inverse function. It's kind of nice. But yeah, every single ordered pair, x comma y, becomes y comma x in the inverse. And if you do that for the equation and then solve for y, you will have the inverse function. In fact, in a moment, I'm going to take the original and I'm going to take the inverse, and I'm just going to show you the visual that we get. Let's zoom that back. Let's go here and clear these out. Come on, you. There we go. And then we get a 5x plus 10. And we get a parentheses 1/5 x minus 2. I'm going to graph them. You know what? I'm going to throw the diagonal in. There's the diagonal, cutting it right down the center, because they are reflections of each other across that diagonal y equals x. Just a visual representation of what we just figured out on paper, which is nice. Now, number 5 wanted to know, okay, hey, are these two functions inverses of each other? Oh, are they? Well, let's see. F of x equals 5x minus 3. G of x equals some weird fraction, x plus 3 over 5. Ooh, are they inverses of each other? I mean, we could graph them, but graphing sometimes doesn't always prove it. We could find all these ordered pairs. Yeah, but you'd have to show an infinite number of ordered pairs. The best way of showing that these two are or are not, because it says determine whether, are they inverses of each other? Well, I'm going to take the composition. And if the composition just results in an x, then yes, they would be inverses of each other. It would be 5x minus 3. So I do a 5 blank, because that's what would be plugged in that blank. I'm going to take the x plus 3 and forcibly shove it in here. What's really nice is that the fraction cancels. 5 and 5 cancel each other out. Divide, multiply, leaving me with x plus 3 minus 3, which leaves me with x. So, number 5, are they inverses of each other? Yes. They are indeed inverses of each other. If you just get an x as a result, then heck yeah, they are indeed inverses of one another. Okay. Let's take a look here. Okay. Now, like I said, I am going to be skipping certain problems. I'm going to go back to my review. Again, that review is available to you on the Google Classroom stream. I am going to be skipping number 7. I'm going to skip number 7, but I'm going to focus in on number 6. The best way of going about a problem like number 6. They want you to graph it, and they want you to state the domain and range. Okay. I can do that. Garbage, blah, 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 blah. One thing that would be best, let's determine where this thing is supposed to start. Let's determine where this thing is supposed to start. Now, typically speaking, H and K are where this thing is supposed to start. It's a little weird to identify H and K on this thing. But normally, the way that you can easily determine what H is by taking what's inside of the square root and setting it equal to 0. That will help you determine where this function is supposed to start in terms of the x values. If I solve this, I get 4. That should be my h value. Now, what is my k value? If you notice, I'm just going to write this above it real quick. I'm making myself a little room here. I'll write this above it. This is your typical square root function, where it was like x minus h plus k. Yeah, I tried to make that a little more bold up top. There we go. But typically, the k value is what's being added to the function, or subtracted, but it's outside of the square root. In this instance, there's nothing being added or subtracted outside the square root, so the k value should be 0. In fact, you can't see it right now. I'm going to move over the camera. But 4 comma 0 should be my starting point. Let me move that over so you can see it. There it is. 4 comma 0 should be my starting point. Because that k value, nothing's being added or subtracted to the square root. But here is where you can utilize your graphing utility. You all have graphing calculators on your computers. Good for you. I'm going to go to my graphing calculator, and I'm going to suggest that you do the same. And I'm going to type in 2x minus 8. Because that is the original function, the square root, I should say, the square root of 2x minus 8. Nothing's being added or subtracted to it, but if there was, I would have to make sure I put that in the calculator. Of course, I could graph this thing right now, but first, before I actually graph this thing, I'm going to go to my table of values. So let's do that. Second graph. Looky there. I get a whole bunch of errors. But those errors actually were expected because, as I stated before, 4 comma 0, right there, what's being highlighted, 4 comma 0 is my starting point. It should make sense because I can't take the square roots of negatives, and if I plugged in that 3, I would get the square root of a negative. I'm going to copy down some ordered pairs here. I'll show you which ones I copy down in a moment. But I'm going to copy down some ordered pairs off of this table of values. I'm not going to copy down all of them. I'm only going to copy down the ones that I believe that I need. Yeah. That looks sufficient. 6 comma 2. Now, 12 comma 4 is like, oh, that's way off. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. 12 comma 4. There we go. You can see that off to the side. Of course, you can confirm, I'm going to draw this curve in a moment, but you can confirm this on the calculator itself if you actually graph it. You can see the direction of that curve. But I need accuracy, and that accuracy that I'm going to get is from that table of values. There it is. There's that nice little accuracy. So you can determine the starting point by solving for h and determining what's being added or subtracted for your k value, as you can see right here. Knowing where this thing starts is a good indicator for your table of values, which you can get the table of values from the graphing calculator. And then when you graph it, I just need to see a bit of accuracy based on the table of values that you got. Now, like I said, I'm skipping number 7, so don't worry about number 7. I don't really care for graphing these inequality things. So I want to jump down to numbers 8, 9, and 10. I'm also going to be skipping 11, just for the sake of argument. I'm going to be skipping 11 as well, so don't worry about number 11. We may double back around to that another day, but not for this major assessment. The problems that I'm skipping are ones that I'm not going to put on the major, just for the sake of argument. Let's talk about numbers 8, 9, and 10. In fact, let me put these on a separate sheet of paper so that we have a little more room to get them done. I know there's a lot of blank space on there, but I'd rather just it be a bit more bold for you guys to be able to see. Here's number 8. Number 8 is the square root of this fraction. Now, in terms of fractions, you can't have square roots in the bottom of a fraction. But what's nice about this is that we are actually allowed to split them up to different square roots. Why? Why, Mr. Markey? Why are you allowed to do that? Oh, I'm allowed to do that because multiplication division is what separates the two terms. Multiplication division. If the operation separating them was addition, subtraction, then I would not be allowed to do this. But because it's multiplication, division, yes, oh yes, I can. 2/7. You have to know when you can and can't separate these terms. This one you can. Let's take a look at number 9. On number 9, you have the square root of 49 x squared y to the, I'm sorry, x squared, that's x to the 6th, y to the 4th. Now, yes, technically, you can split each of these terms up to their own individual square roots because there's multiplication separating them. It is a square root because there is no little number in that little crevice. What escapes the square root is a perfect square. Well, 49 is already a perfect square. It's 7 squared. In fact, x to the 6th contains a bunch of x squareds, and y to the 4th contains a couple squareds. I'm going to zoom out and show you that. There we go. Technically, everything within this square root is a perfect square. It doesn't look like that at the beginning, but once you break that thing apart, there it is. Everything escapes. In fact, the 7 escapes. 3 x's escape, but keep in mind those 3 x's are being multiplied together. So it should be x cubed. And those y's escape. That's your simplified answer. Let's take a look at number 10. Now for number 10, you have the cubed root. This is going to get a little crazy. The cube root of 24, a to the 6th, b to the 5th. Now, it's going to act in a very similar fashion to number 9. But it's a cube root, which means the only way you're going to escape is if you are a perfect cube. Now, in this instance, 24 is not a perfect cube number. 24 does contain a perfect square, but what else does it contain? I know I can divide it by 4. Oh, I guess I just got to break this thing down. It doesn't take that long to figure out that you could take 24, divide it by 2, divide it by 2, divide it by 2, divide it by 3. Doesn't take that long to figure that out. So when you rewrite this cube root, move this up a bit, this 24 is actually 2 cubed times 3. I could take that a to the 6th and I could break it up a cubed and a cubed. Again, the reason is because it's a cube root, and the only way you escape a cube root is with a perfect cube. The b to the 5th, well, I can break it up b cubed, b squared. Move that over. There we go. This cube can escape, or not the cube, but the 2. This a can escape, this a can escape, and this b can escape because they have the proper exponents. The 2 escaped, an a and an a escaped, and a b escaped. But that extra b, 3, and that extra b squared, unfortunately, could not. They're left behind. Sucks to be them. Sorry, goodbye. That's what those things should be. Oh, happy day. Okay. Let's try to break this thing down a little bit more. or not this thing, but the next problem, I should say. Number 11, I'm going to, as I said before, just skip number 11. Don't worry about that. Number 11 is not going to be on your major. But let's take a look at number 12. Let me zoom in on that. Now, again, can't read it. Oh, man. Good thing the PDF of this is available in your Google Classroom. So you don't have to strain your eyes at the screen. Number 12. The diameter of a tree is related to its basal area by that formula with a square root. If the basal area, BA, of a tree is 12.4, what is the diameter of the tree? This is just making sure that you're able to use the calculator appropriately. I'll show you what I would do in my calculator in a moment. Sometimes I may give you a problem like this, and I would give you the diameter. And then you would have to solve for the basal area by peeling off those layers. But this problem has given you the basal area. So I would go to my calculator. I would go square root of 576 times 12.4 divided by, now they specifically said to use 3.14. I would disagree with that personally. I would actually try to use the real pi, but I'm sticking with what the problem said. 47 point, oh, it says 3 places, 693. I'm sticking with what the problem says. But keep in mind, you can't just leave that number there and say that that is the answer. You're going to have to give me proper units. And the units on that problem, let's say that's the diameter. Inches. Says it right in the problem. Nice. Okay. Let's take a look at number 13. Now, number 13 wants you to write that radical using rational exponents. Now, what that means is this. Power over root. Power over root. There are a bunch of different ways to handle number 13. A bunch of different ways. Let me write this down on a separate sheet of paper. Zoom out, zoom out. There we go. The fifth root of 32 m cubed. Now, keep in mind that this particular problem did not ask you to simplify. You could simplify it because 32 is a very special number. You can divide it by 2 5 times. 32 is actually 2 to the 5th power. So there's a way of handling that. But the problem wanted you to write the radical using rational exponents. So what the heck does that mean? Done. Literally done. Now, like I said, there's a whole bunch of things you could do to this problem. In fact, I'm going to do one of those things to the problem in a moment. I'm going to do one of those things. But that's one way of doing the problem. They wanted you to write the radical, which was the 5th root. They wanted you to write that radical using rational exponents. Well, a 5th root is nothing more than a 1/5 exponent. Power over root. Now, some people would try to take that 3 out. Yeah, but that 3 would have to be the same on the m and on the constant. It would be. Unfortunately, that doesn't work. Because remember, power of a power, you would have to multiply the exponents together. So let me rewrite this problem. Remember I said I was going to do something to it. what I just did right there. I changed the 32 because I knew that the 32 was 2 to the 5th power. Zoom out a little more, a little more, a little more. There we go. I can distribute the 1/5 because multiplication is what separates those two terms. And if I do that, that would be 2/5 to the 1/5. Multiply those, it just becomes 2. 3 to the 1/5. That should be m to the 3/5. You can either write your answer like this, because it does satisfy the directions, or if you go a bit farther, you can write your answer like that, because it also satisfies the directions. They wanted you to rewrite the radical using rational exponents. Rational exponents are nothing more than fractions. Technically, the bottom one would be simplified, but that's not what the problem asked for. Number 14 does ask for you to simplify. There we go. Let that thing focus for a moment. There we go. Number 14 does ask for you to simplify, which is nice. Now, in this case, oh man, I got 3 x's floating around here. Maybe I could combine them. But just like with radicals, the only way I can combine them is if they have the same root. I mean, on the bottom of that fraction, it looks like a square root and a third root. Ugh. If only there was a way to make common roots. Power over root. If only there was a way to make common denominators. Of course there is. Of course there is. You can make a common denominator on this problem. Move that up a bit. There we go. By making this x to the 6/6 power. Move that down a tiny bit. There we go. Divided by x to the 3/6 power times x to the 2/6 power. You can make each term have a common denominator of 6. And then ultimately, yes, when you multiply common bases together, you are to add their exponents. And when you divide common bases, you are to subtract their exponents. Ultimately, the final answer to this problem can be written like that. X to the 1/6 power. Because technically it would be 6/6 minus 3/6 minus 2/6. They all have a common denominator. That makes them a common radical of the 6th root. And then we just combine in the proper fashion. We combine the numerators. Oh, it's nuts. Number 15, I'm going to do with you in a moment. Number 15, I'm going to do with you in a moment. Number 16, I'm just going to cross out real quick, because number 16 is not something that I'm going to be putting on your major. So you can cross out number 16. Goodbye, 16. But I am going to be doing number 15. So bring back a paper. I'm going to rewrite number 15. Rewrite it right here. If I could zoom out a bit. There we go. Number 15 is the 3rd root of 3m plus 1 equals 4. This is more akin to what we've been doing for the past several class periods, solving these radical equations. First, if I'm going to be solving for x, getting x by itself, recognize the fact that there are parentheses around this 3m plus 1. Then I'm going to be doing PEMDAS backwards, meaning parentheses should come last. There's no outside addition subtraction. There's no outside multiplication division. Instead, I'm going to be dealing with that exponent by cubing both sides. If I cube the left side, 3m plus 1 just pops out. And if I cube the right side, I get 64. Then it's just like a pre-algebra problem. Subtract 1, divide by 3. The answer should be 21. And it is. You could plug that sucker back in. 3 times 21 is 63. 63 plus 1 is 64. The cubed root of 64 is 4. Because 4 times 4 times 4. Weird. Then we roll right into a word problem. Number 17. Now, like I said, I am going to be skipping number 16 there, but I do love myself some word problems. The velocity of v in feet per second of a roller coaster at the bottom of the hill, oh, I can't even take this, Mr. Markey, why are we reading this, is related to the vertical drop in feet and velocity, oh my gosh, in feet per second of the coaster at the top of the, Mr. Markey, I stopped listening when he said the velocity, by the formula v sub 0 equals the square root v squared minus 64h. Here's what you need to know. V is the velocity at the bottom of the hill. H is the vertical drop. Height, most likely. V sub 0 is the velocity at the top of the hill. These are just variables. That's all they are. They give you some numbers in that question, and we just have to plug them into the appropriate location. They want to know what velocity must a coaster have at the top of the hill. Well, the variable that relates to that is v sub 0, the velocity at the top of the hill. They want to know what is v sub 0. At the top of a 150-foot hill, 150 is the value of h. You have to plug that into the appropriate location. What velocity must a coaster have at the top of the hill in order to achieve a velocity of 100 feet per second? So they want to know, what do I have to have at the top in order to get 100 feet per second? They don't say it, but most likely at the bottom. Which means V is equal to 100. So let's see. Let's plug that sucker in. Let's see what happens. The hardest part about word problems is just recognizing what the heck it is that they're saying in the first place. 100 squared minus 64 times 150. You have to make sure that it's typed in correctly. You have to make sure that the order of operations are followed correctly. If you want to, you can actually evaluate the inside separately and then square root that result. But that's what the answer should be. Keep in mind, I need proper units. That's measured in feet per second. They're basically saying that you need to have a velocity of 20 feet per second at the top of the hill. You drop 150 feet, and then that momentum will carry you to 100 feet per second, according to that formula. 20 feet per second. Again, please be very careful with word problems. Number 18, I'm going to do on a separate sheet of paper. because I need a little more room for that than what they gave me. They want to know, what is the square root of 34 over the square root of 51 in simplest radical form? Ugh, that's gross looking. Let's break this thing apart. First, let me break the 34 apart. 34 divided by 2 is 17. So this really should be the square root of 2, the square root of 17. Okay, 51. 51, I can't divide it by 2, but I can divide it by 3. And when I divide it by 3, I get 17 as well. This should be the square root of 3 and the square root of 17. Ms. Markey, are you allowed to break it up like that? Yes. Because it's multiplication division. The square roots of 17 cancel each other out, leaving me with the square root of 2 over the square root of 3. But, as I've stated in the past, you can't have a radical in the bottom of your fraction. So, this is one of those weird situations where I'm going to multiply like this. Technically, I have multiplied by 1 because the square root of 3 divided by the square root of 3 is just 1. So I'm not changing the value of the number. But the reason why I'm doing that is because I need to get rid of the square root in the bottom of the fraction. And the only way you get rid of a square root is with a perfect square. So by multiplying by a square root of 3 on the bottom, this becomes, well, on the top, it becomes the square root of 6, because 2 times 3. And on the bottom, it becomes the square root of 9, because of 3 times 3. Oh, the square root of 9. It's just 3. That would be the proper way of simplifying that problem. Zoom out a little more. Show the original. That would be the proper way of simplifying that problem. I'm going to go over number 19. Number 20 is fairly straightforward. Number 20 is very similar to number 12. You just have to know how to type that in correctly. Don't worry about the bonus. Bonus is not my prerogative whatsoever. But I'm going to wrap up with number 19. Number 19, a triangle has that base and that height. Find the area. Ugh. Oh, 1/2 base times height? Yeah, 1/2 base times height. So, number 19, 1/2 base times height. There's a lot of power over roots going on here. But you have to combine those terms if they have common bases. First of all, 1/2 times 6 times 8 should give you 24. 1/2 times 6 times 8 should give you 24. So it should start out as a 24. R to the 1/2 times R to the 1/2. Well, they already have a common denominator of 2. So that really should be R to the 2/2. I'll simplify that in a moment. And the t, well, 3/4 plus 3/4 should give you 6/4, which I will simplify in a moment. This really should be 24r t to the 3/2 power. Heck yeah. You have to know how those exponents are working out. I'm going to wrap it up there. Like I said, this review is available to you in the Google Classroom stream, so you don't have to strain at the camera in order to get these questions down correctly. I am going to be assigning you a major before the end of this week, which you will have part of the weekend to get done. On Friday, we will be starting a new chapter, so get ready. But if you do have any questions in regards to that major, obviously I will talk to you more about that on Friday because you will have part of the weekend to get that done. But if you have any additional questions in regards to this review, of course, you can email me separately and we can figure out a time to talk about that. If you have not left a comment in the chat, and I can see all your wonderful little comments right there with your timestamps. If you have not left a comment in the chat, please make sure that you do so. I'll give you a moment to do that, but otherwise, I am going to be signing off. Everyone enjoy their Wednesday. I heard there's going to be some weird weather the next couple of days. I just want winter to be over. We all need to get outside. Anyway, y'all have a wonderful day, and I will see you on Friday.